Hello everyone, this is Professor Ng Ji Kum from Unimas. In this video, I'm going to give you a lecture on absolute maximum shear and moment. So in the previous lecture, we have already learned how to calculate the shear and bending moment at a particular point due to moving loads. Okay, so in the previous lecture, we only looked at specific points. In this lecture, we're going to look at how the arrangement of load on a beam, okay, will affect the maximum shear or maximum moment at a particular point, okay, not at a specific point, but now we want to look at where it happens when we have a series of arrangement of forces. Okay, so a more general problem involves the determination of both the location of the point in a beam and the position of the loading on the beam so that one can obtain the absolute maximum shear and moment caused by the loads. Okay, so for shear, okay, so shear in cantilevered beam, the absolute maximum shear will occur at the point just next to the fixed support. So the maximum shear will occur in a cantilevered beam at a point where it is very near to the fixed support, where this distance may be considered as 0. Okay, so after you have put on the forces like this, so these forces can be anywhere on the beam. The shear force will be the same at this point. Alright, okay. And then for simply supported beams, the absolute maximum shear will occur just next to one of the supports, right? So meaning that you have to put this system of forces with the force at the end here very near to the support. Okay, so this will give you the maximum shear at this support here. Alright. Okay, so this distance is very close to this support already, but before it reach this support here, okay, and then the maximum shear on this side may be obtained by putting this system of forces with this force very near to this support here. Okay, so move all these three forces with this force very near to this support to get the maximum shear force at this support. Alright, so this type of beams, okay, for shear, we can get the values by just visual inspection on how we arrange the loads. Okay, and then for moment, okay, the absolute maximum moment for a cantilevered beam occurs at the point where absolute maximum shear occurs for a cantilevered beam. Okay, so for cantilevered beam, the point where you found the maximum shear is the place that you will find the absolute maximum moment. Okay, but in this case, you have to place the system of forces with the end force here at the tip of the cantilever. Okay, so this will maximize the moment at the fixed support there. Okay, so as I mentioned just now, the concentrated load should be positioned at the far end of the beam, okay, with the end force here, okay, very near to the tip, so this distance can be considered as 0. Alright, and then for moment, in a simply supported beam, the critical position of the loads and the associated absolute maximum moment cannot, in general, be determined by inspection. Okay, so in this case, we cannot tell where the absolute maximum moment will occur. Okay, and we also don't know how are we going to arrange the loads at which position. Okay, so in this case, the position of the loads can be determined analytically. So we have to do some analysis on how we are going to position the loads and where the absolute maximum moment will occur. So, consider a beam subjected to forces F1, 2 and 3 like this on a simply supported beam. Okay, so the moment diagram for a series of concentrated forces consists of straight line segments having peaks at each force. So we have learned this in strength of materials already. So if we have a series of forces like this, then the bending moment diagram will look something like this. Okay, where the peak of the moment will happen on one of the force location. Okay, so in this case, we assume that the absolute maximum moment occurs under force F2. So we are going to assume that the maximum moment occurs under this point load here, which is F2. Okay, so the position of the three loads on the beam will be specified by the distance x measured from F2 to the beam's center line. So now we have to measure the distance okay, of each of the load from the center line of the beam, okay, where F2 has a distance of x. Okay, so before we start, we need to find the magnitude of the resultant force from these three forces. Okay, and also the location of the resultant force also. Okay, so meaning that we need to find what is the distance of this resultant force. Okay, and then we need to find out what is the magnitude of the resultant force as well. Okay, so for the magnitude Fr, okay, it is just F1 plus F2 plus F3, as you have learned in engineering mechanics. Okay, and to find out the distance of x bar, okay, now I am using this point as the reference point. Okay, so if I use this point as reference point, then I just find out what is the moment caused by each of the forces with respect to this point. Okay, and then the moment caused by all these F1, F2 and F3 about this point must be the same as the moment caused by the resultant force Fr multiplied by the distance x bar to this point. Okay, so this is something that you have also learned in engineering mechanics. So in this case, when we use this point as the reference point, okay, so F1 to this point is 0 distance. Okay, so there is no moment caused by F1. Okay, and then the moment caused by F2 to this point here is F2 times D1. Okay, so we have F2 multiplied by D1, and then we have F3. Okay, and the distance of F3 to this point here is D1 plus D2. Okay, so we have to 8F3 times D1 plus D2. Okay, so there is no other forces causing moment in each of the respective forces. Okay, so now we equate these to the moment caused by the resultant force Fr, okay, to the reference point here. Okay, so the moment caused by Fr to this reference point is Fr multiplied by x bar. Okay, so Fr multiplied by x bar, okay, is the moment of Fr respect to this reference point. Yeah? Okay, and then just now we have F2 times D1 plus F3 times D1 plus D2. Okay, so we'll get x bar is equals to F2 D1 plus F3 D1 plus D2 over Fr. Okay, so this is something that we have learned in engineering mechanics. So this is just a revision. Okay, so next we'll see that what happens to the moment. Okay, so before you can calculate the moment, okay, we have to determine the reactions. Okay, so in this case we are going to determine what is the reaction AY due to this arrangement of load. Okay, so now we assume that the maximum moment or the absolute maximum moment will occur underneath F2. Okay, so we define the distance from the center line of the beam to F2 as x. Okay, and then we define the distance from the resultant force Fr to F2 as x bar prime. Okay, so meaning that this distance is x bar prime minus x, right? And then the distance from F1 to F2 is D1. This one is fixed, it doesn't change because it is the same as in the system of forces. Okay, and then the distance from F2 to F3 is D2. So these are fixed values, they don't change, right? And then this is the center line of the beam, so meaning that this distance is L over 2, this distance is also L over 2. So now to find out what is AY, okay, we assume that AY is in the upward direction. Okay, so if we want to find out what is AY, okay, then we can sum moment at point B, right? Okay, so we just sum moment at point B. Okay, so when we sum moment at point B and we take anti-clockwise moment as positive, okay, then we are going to have AY times L, which is negative. Okay, so we will have negative AY times L. Okay, and then technically speaking, we need to find out what is the moment caused by each of these forces. F1 times this distance. Okay, and then we have to find out what is F2 times this distance to point B, and F3 times this distance to point B. Okay, but in this case, we have already determined the location of Fr and the magnitude of Fr already. So this is the resultant of these three forces. So in this case, this resultant force will represent the three forces, right? So it represents F1, F2, and F3, yeah? Okay, with this Fr here. Okay, So meaning that the three forces here, okay, the three forces here will be replaced by only this force on the beam. Okay, so instead of calculating the moment caused by these three forces, we just need to calculate what is the moment due to this resultant force. Okay, because this resultant force represent these three original forces. Right? So in this case, we have Fr times this distance. Alright, so we have plus, because this Fr is going down, so it will cause an anti-clockwise moment about point B. We have Fr, okay, multiplied by L2 minus x bar prime minus x. Okay, so we have x bar prime minus x. Right? And then there is no other forces causing moment about point B, then we can equate that to 0. So once you solve for this, okay, you'll find that AY is 1 over L times FR times L over 2 minus x bar prime minus x. So this is the solution for AY. Okay. So once we have solved AY, then we can cut across the section, okay, at the force F2 there, because we assume that we have the maximum moment at F2. So F2 is originally here, okay. So just now we say that we assume that the absolute maximum moment occurs under F2, okay. So now we cut across a section at F2 and find out what is the bending moment there. Okay, so when you cut across this section, it will look like this. Okay, with this distance equals to D1. So F2 is actually exactly here. So we don't need to put in F2 here because it doesn't affect the bending moment that we're going to calculate. Okay, so if we cut across this section here and call the shear force V2 and call this moment M2, okay, and then this distance is L2 minus X. Alright, so now we want to find what is M2. So to find M2, we can sum moment over here. So meaning that this V2 will not appear in the moment equation. Alright, so if you sum moment here, then we have M2 equals to AY times this minus F1 times D1. Okay, so you are not familiar with how I did it, then you can write total moment equals to 0, and then we have M2, okay, minus AY times L over 2 minus X plus F1 D1 equals to 0. Okay, so this is the sum of moment equation, right, where we have equilibrium equals to 0 here, and then if you solve for this, then you end up with this. Okay, and then if you substitute AY equals to 1 over LFR, L over 2 minus X bar prime minus X, okay, then you expand it and you are going to get this expression here. Alright, okay, so in order to get the maximum value of M2, okay, we need to differentiate M2 with respect to X. So the M2 dx you will have a constant, so when you differentiate this, it becomes 0. When you differentiate this, it also becomes 0 because x bar prime is a constant. Okay, so the only variable is x. Okay, so you differentiate this, you're going to get minus 2 frx over L, and if you differentiate this, you're going to get frx bar prime L, and then this is a constant. After differentiation, it becomes 0. So we're left with these two terms here. Okay, okay, and then to get maximum moment, we have to set dm dx equals to 0. Okay, so solve for this, you're going to get x equals to x bar prime over 2. Okay, so meaning that this distance x from F2 to the center line of the beam is actually half of x bar prime. Okay, so what this means here is that the absolute maximum moment in the simply supported beam occurs under one of the concentrated forces such that this force is positioned on the beam so that it and the resultant force of the system are equidistant from the beam's center line. So it's quite a mouthful here, but what it means is that if we assume one of the forces positioned in the beam in such a way that it will produce the maximum moment underneath this force. So the distance from this force to the center line is half of the distance from this point force to the resultant force. So meaning that x is equals to half of the distance from this point force to the resultant force. Alright? And then this is another method of determining maximum values of moments. So in this case, we are going to select a few points on the beam. Okay, so in this case, on the beam, probably we will select the, normally we start with the midpoint of the beam, where 1 point force put here will create maximum moment at the beam at the center line. So you draw the inference line for this beam at this point here, and then determine what is the maximum moment due to this system of forces. And then you select another point. Okay, you draw the inference line for the moment again, and then determine what is the maximum moment due to this system of forces with respect to this point, right? And then you select another point and repeat the process. Okay, it's quite a tedious process. So you have to select a few points on the beam and then draw the inference line for the respective location. Okay, and then determine what is the maximum moment due to this system of forces at each respective point. Right, and then you plot the graph and determine where is the location of the maximum moment due to this system of forces, right? So in that case, you have to do a lot of analysis, okay? A lot of inference lines to draw, okay? You have to draw inference line for at least 3 or 4 points, and then determine the maximum moment due to the moving load on each respective case. And then you plot the graph to see where you get the peak maximum moment. Okay, as opposed to the method that we have discussed just now. Okay, this one you just need to do 1 or 2 analysis and you will get the absolute maximum moment. So now let us look at an example. Okay, so in this example, you're asked to determine the absolute maximum moment in the simply supported bridge deck shown below. So the bridge deck has a 9-meter span. Okay, and then we have a vehicle okay, uh, towing something behind, okay. So the front wheel axle will exert 8 kilonewton force, and the rear wheel axle will exert 6 kilonewton force. And then in the turning part, okay, we have 4 kilonewton force exerted by the axle of the wheel. Okay, so first of all, to solve this problem, we have to find out where is the resultant force of all these three forces. Okay, so in this case, we are using this point C as our reference point. Okay, so in this case, we have this 8 kilonewton force passing through point C, so the moment caused by 8 kilonewton force is 0. And then this 6 kilonewton force has a distance of 3 meter, so the moment is 6 by 3. And then this 4 kilonewton force has a distance to C of 4.5 meters, so it causes a moment of 4 times 4.5 meters, right? And then the resultant force is 18 kilonewton. Okay, so 18 times the distance x bar to the reference point here, okay, should be equals to the total moment caused by the system of forces. Okay, so from here we solve x bar is equals to 2 meter from C. Alright. Okay, so after we have determined the location of the resultant force and the magnitude, then we can place the force or the system of forces on the beam. So now we first assume that the absolute maximum moment occurs under the 6 kilonewton load. Okay, so the 6 kilonewton load is here. The resultant force is at 1 meter away from this 6 kilonewton force. So if you assume that the absolute maximum moment occurs underneath this load here, okay, then we have to place this system of forces in such a way that the distance from this point load, where we assume that the maximum moment will occur underneath it, okay, with the equal distance to the center line of the beam with the resultant force. So this distance must be the same distance as this. Okay. So the distance from the resultant force to 6 kilonewton force is 1 meter. So meaning that this distance must be 0.5 meter. So this is 0.5 meter. Alright. And then the beam total length is 9 meters. Okay. So to the center line is 4.5 meters. Okay, so in this case, the resultant force to this 8 kilonewton force is 2 meter. So meaning that this is 2 meter, right? And then this is 1.5 meters, okay? And this is 0.5 meters, right? So with this arrangement of load, okay, now we want to determine what is the reaction AY, okay? So to determine reaction AY, we can sum moment at point B. Okay, so now this resultant force can represent all these three forces. So in this case, when we sum moment, okay, we get rid of these three forces. Okay, and then the remaining force will be just the resultant force. Okay, so when we sum moment and take anti-clockwise as positive, then we have minus AY times 9, okay, plus 18 times 5. Alright, because this is 4.5 and then this is 0.5. So the distance here is 5 meter. Okay, and then there is no other forces. Okay, remember that all these three forces are represented by the resultant force. Okay, so we don't consider them anymore when the resultant force is there. Okay, so then we equate this to 0 and then we find that AY is 10 kilonewton. Okay, so in this case we assume that the absolute maximum moment occurs under the 6 kilonewton load. So we assume that the maximum moment will occur here. So for that we just cut across this section, okay, and isolate this part of the beam as a free body diagram, and we are getting this diagram here. Okay, so whenever you cut across a section there must be a shear force and a bending moment there. Okay, so we put all the shear force and bending moment in the positive direction. Okay, so these are the shear force and bending moment in the positive sign convention, right? Okay, so we just measure all the distance of the forces, okay, in this case, and then we know AY is equals to 10 kilonewton from the analysis. So now we just sum moment at this point S here, okay. So if we sum moment here, then we're going to get minus 10 times 5 plus 8 times 3, okay, plus ms equals to 0. So if we solve for ms, we are going to get ms equals to 26.0 kilonewton meter. Okay, so we have to check whether this is the maximum moment or not. Okay, because we have another case when we assume that the absolute maximum moment will occur under the 8 kilonewton load. Okay, because this resultant is in between 6 kilonewton concentrated load and the 8 kilonewton concentrated load. Okay, so we don't know whether the maximum moment will occur here or it will occur there. Okay, so we have already solved for the maximum moment when we assume that maximum moment occurs under 6 kilonewton just now. So now we want to analyze for the case where we assume that the maximum moment will occur under the 8 kilonewton load. Okay, so we assume that the maximum moment is under this 8 kilonewton load. Then we have to put the arrangement of forces in such a way that the 8 kilonewton load and the resultant force has equal distance to the center line of the beam. Okay, so just now this distance from this 8 kilonewton load and this resultant force is 2 meters. So meaning that you have to put the forces in such a way that 8 kilonewton is 1 meter away from center line and the resultant force is 1 meter away from the center line also. Okay, so with this arrangement of load, okay, we can calculate what is the reaction of AY by summing moment here. Okay, so the summation of moment here will yield minus AY times 9 plus 18 times 3.5 equals to 0. Okay, you notice that the 8 kilonewton force, the 6 kilonewton force and the 4 kilonewton force does not appear in this moment equation because they are already represented by this resultant force Fr, which is 18 kilonewton. Okay, so from this we solve for AY and we get 7 kilonewton. Okay, so now we want to cut across a section here because we assume that maximum moment occurs here. So you cut across this section and isolate this part of the free body diagram as the free body diagram of the beam. So we are getting this diagram here. So AY is 7 kilonewton as we have solved just now. And then once you cut across the section, we have shear force and bending moment, and we put them in the positive sign convention. Alright, and then from this free body diagram here, we just sum moment at point S here. Okay, so we sum moment here, then we're getting minus 7 times 3.5 plus ms equals to 0. So ms in this case we get 24.5 kilonewton meter, which is less than the case when we assume the maximum moment is under the 6 kilonewton force. So meaning that the absolute maximum moment occurs underneath or under the 6 kilonewton force, which is 26 kilonewton meter, when the arrangement of load is something like this. Okay, so you get 26 kilonewton meter of bending moment under the 6 kilonewton force. Okay, so that's all for this lecture. Thank you very much for listening.